Okay, so let's look at this question here. It's an interesting mix of stoichiometry and organic chemistry. It says to you 1 mole of CnH2n burns completely in 192 grams of oxygen according to the following unbalanced equation. Balance the given equation and determine the molecular formula of CnH2n with the aid of a calculation. Okay, so the first thing to do is to balance the equation. So if you understand how balancing equations works, this is not too hard, even though we are dealing with the variable n instead of an actual number. So if we have a look here at this equation, okay, there's carbon on the left and there's carbon on the right. All of the carbon in the products comes from this carbon in the molecular compound. So how much carbon do we have on the left hand side? We have n atoms of carbon, so we are going to end up with n atoms of carbon on this side. Then we look at the hydrogen, and all the hydrogen has come out of here, and this has got 2n atoms of hydrogen, and water has 2 hydrogen atoms per oxygen. So if there are 2n over here, they will end up being n hydrogens on this side, because if you remember that you multiply the coefficient by the subscript to find out how many atoms you've got here. So here the subscript is 2n, okay, and here the subscript is 2, but if we multiply it by the coefficient, we will also have 2n. So now we're just left with the issue of trying to resolve the oxygen. Okay, so if you have a look here, there are 2 oxygen atoms here, and there's 1 oxygen atom over here, and over here there are 2 oxygen atoms. So I've got 3 on the right and 2 on the left. So to balance this correctly, it's going to be, we need 1.5 of these, okay? So now this is not how we normally balance equations. We don't normally have a 1, a 1.5, an n and an n. We normally double everything up. But the reason why I'm not going to double it up is because it says to you 1 mole. So we want the coefficient on this hydrocarbon to be 1. So I'm going to leave the coefficient on the water as 1.5. Okay, so we've balanced this equation. If you wanted to balance it completely, you could go 2 of these, 3 of those, goes to 2n of those, and 2n of those. But we're just going to leave it like this to determine the molecular formula. So then the next thing that we have to do is, as we always do, have to find the moles. So n equals little m over big M. So what are we finding the moles of? We are finding the moles of the oxygen. So we should actually write this properly like this. The number of moles of oxygen is little m over big M. So the little m is 192, and the big M, 16 plus 16, is 32, which gives you 6 moles, okay? 6 moles of oxygen. Then if we look at our mole ratio like we do in all calculations, if we go the mole ratio of the hydrocarbon to the oxygen, it's 1 is to 1.5, okay? 1.5, that is not 1.5 I wrote there. 1 is to 1.5, and currently I have 6 moles of water. So if you have to work this out, it works out that you're going to, if I assume you can do the ratio calculation without me holding your hand. So this becomes 4 CnH2n like this, okay? But it's not actually 4 moles. It would be 4 moles if they were moles, but this becomes the little n number that we don't know. So it becomes C4, and then the H is 2n, C4H8, which, as you may realize, is but something or the other. Is it butane, butene? We would have to check it out. I can't remember. Okay, but go back and check. Go back and check here. If I have C4H8, okay, and then I have 1.5 moles of oxygen, will I end up with 4 moles of carbon dioxide and 4 moles of water? And if the answer is correct, yes, then, oh wait, rub this out here, not the 1.5. We want to turn this into the 6, yes? Okay, if this turns out to be 6, then we've got the correct equation, but I'm pretty sure that it is butane C4H8.